Hey everyone, and welcome to today's session all about Megascans, where we're going to take a behind-the-scenes look at some of our production pipelines and improvements that we've been working on. My name is Richard, and I'm the lead pipeline developer at Quixel. My team and I are responsible for all of the scan post-processing tools that process the data, as well as defining the workflows and procedures for new asset types as they're introduced into the library. We're going to take a deep dive into several exciting areas today, from scanning techniques to processing methods to some of our automation tools that have helped us scale up production over the years. But before we get into that, and for anyone who's maybe new or doesn't have much experience with Megascans, what is it and how can you get the most out of it in your own projects? Well, Megascans is a comprehensive library of photorealistic assets created by scanning real-world objects and surfaces from all over the world. Our extensive collection covers dozens of unique biomes and includes detailed vegetation, natural surfaces, as well as man-made structures, props, and so much more. This makes them particularly valuable in areas like games, VFX, automotive, and architectural visualization, significantly cutting down the time and effort required to create lifelike environments from scratch. Being integrated into the Epic ecosystem means that we're committed to providing premium, scalable content that benefits all creators, from large studios to independent creators. Our assets empower teams of every size to streamline their workflow, enabling everyone to reach their creative goals effectively and efficiently. So we have a diverse collection of assets from all over the world, but we also have a diverse collection of asset types, which are all designed to be used together in your scene. Our 3D assets form the backbone of detailed world building, and they offer a wide range of props and elements to fill your environments. This lets you stay in your creative flow, focusing less on asset creation and more on creativity. Our modular assets act like building blocks designed for grid snapping, as well as use in parametric tools. And then we have specialized vegetation assets. These are built from individual scan elements and then handcrafted into realistic, lush plants with age and health variants, to name just a few of the parameters. And then we have full 3D trees, which are some of the most complex assets in our entire library. These are complete trees constructed entirely from real-world scan data and then combined with powerful procedural systems which perfectly complement our smaller vegetation assets. Things like wind, seasonality, and health can all be controlled from a single blueprint actor, allowing you to tame the natural world with just a few clicks. Our surface assets are highly detailed scan texture sets, ideal for any surfaces, terrains, and even props that you may want to retexture. These are seamless, tileable, up to 8K, and ready to use in a variety of settings, from high-resolution textiles to automotive materials to the natural and built environment. And then we have additional categories like atlases, decals, and imperfections. Atlases are a collection of smaller scanned elements for things like foliage creation or debris scatter. I won't go into too much detail today with these, but these come from our photometric scanners, which effectively analyze the light patterns in the scan and infer PBR surface details. Then we have decals, which easily add surface details like dirt, damage, and graffiti to your scenes. And then finally, we have imperfections, which are very subtle textures designed to enhance realism and final visual polish for your scene. Perhaps best of all, we also offer detailed sample projects designed to demystify the scene creation process, showing how Megascans content can be leveraged in various workflows, utilizing numerous asset types together. These projects provide insights into creative applications and practical examples of our scan content in real-world scenarios. And the best thing about these is that they're available absolutely for free from fab.com. So when it comes to content, your feedback really matters to us. So if you scan the QR code on the slide, you can access our entire content roadmap. So we would love to know what types of assets and content you would like to see in future. So please do share your thoughts, as your input helps to shape the direction and development of Megascans, so we can provide content that is relevant and useful and exciting to you. I'll give you a few more seconds for that. All right. So today's focus, we're going to look at a few different things. We're going to take a look at capture tech and best practices when out in the field. We're going to look at tools and workflows, the improvements and standards that we've developed as we've shifted over to Fab. And then finally, our ongoing focus on education and our commitment to enable anyone to become a creator. So to start with the scanning step, our scanning process begins long before we capture any data. We carefully plan trips, considering critical factors like ideal locations, permits, weather conditions, seasonal limitations, and as well as asset value within the library. To capture the highest quality data, we use a custom-built hardware rig with the DSLR camera, 2 flashes, polarizing filters, as well as a backpack containing a large battery pack so that the scan team can be out in the field for hours at a time. We refer to this setup as the flash scanner, and I'll refer back to it later. Right now, our scanning fleet mostly consists of Sony A7R III cameras, which has been our workhorse for the last few years, which shoots roughly 42 megapixel images. The number of images per scan varies dramatically on the type of scan we're doing, but it could be anywhere from a couple hundred to several thousand images. The flashes on the rig allow us to cancel out any ambient lighting and shadows that may be present at the time, and the polarizing filters are placed both on the flashes and the camera, orientated at 90-degree offset. This arrangement produces cross-polarized images that capture only the base color, removing any specular reflections and other reflectance components. Throughout the entire scanning workflow, we follow rigorous best practices to make sure that we get even coverage, as any issues with the scan will show up later in the process, and it's generally takes way longer to fix down the line than on site. On the calibration side, we ensure that all scans include a Macbeth color chart and a custom scale marker. This gives us critical data when calibrating our scans later on. The color checker ensures accurate color calibration and reliable white balancing, resulting in true-to-life color representation without introducing subjective biases. There could be subtle ambient lighting on the day that is almost enough to overpower the flashes, or settings on the camera which maybe change the calibration. So having that data is really important for us. And then the inclusion of scale markers allows us to capture precise dimensions, resulting in a one-to-one version of the asset with no guesswork about the scale of the asset afterwards. In the top image, you can also see a red laser guide. This is actually from 2 lasers which are attached to the rig, which converge and align with each other at a certain distance away from the rig. Because we're using flash scanners, we need to account for the fall-off of light. So the fall-off of light over distance when scanning. So the scan artist knows that as soon as those 2 markers line up with each other, that's the right distance away. So that's a calibrated distance. During scanning, we use a proprietary mobile app to register every asset, ensuring that each receives a unique ID right as it's captured. During registration, we attach essential reference imagery, detailed notes, and necessary legal information, all of which streamlines the asset management process. This is critical when dealing with potentially hundreds of assets per scan trip and potentially thousands or tens of thousands of assets in the library. After scanning, the asset data is uploaded to the cloud, allowing it to pass through our post-processing tools. To support a collaborative workflow, each processing stage generates new data that's uploaded back to the cloud, allowing subsequent stages to seamlessly download and continue processing by different teams. The centralized application is used for tracking all of our assets from scanning through to final delivery. In this next section, we'll take a look at the differences between raw photogrammetry results and the Megascans assets, as well as some of the steps that we take to bridge the gap between the two. So to start off with, all of our photogrammetry-based assets, we rely on reality capture to process the images into 3D meshes. For Megascans production, our goal is to always find the best balance between quality and efficiency. Instead of working with extremely high-resolution meshes with billions of triangles, we optimize our process to use high-detail meshes capped at around 300 million triangles. This mesh density provides ample geometric detail, allowing us to confidently generate high-detail assets with 8K texture maps. Additionally, we export a secondary mesh at 50 million triangles, specifically set up with UVs for hosting a 32K base color map, which we can then bake to the final asset later on. So in this example, we can see an asset directly from reality capture with crazy high geometric detail, but also highly fragmented UV islands, which make it unsuitable for real-time applications. So now let's take a look at some of the key factors that differentiate Megascans from raw photogrammetry outputs. The main points that I'll cover here will be IP compliance and the importance in our production environment, additive reconstruction and some of the techniques that we use to get great results in unforgiving scan environments, texture enhancement and the role that PBR map authoring plays in production, and finally we'll look at cases where we need to heavily modify scans to become flexible modular assets. So one of the most important considerations is the legal review process. IP compliance is critical for ensuring that our scanned content is safe to use in commercial projects like games, films, and any content that gets sold on fab. Common IP issues include barcodes, labels, brand names, distinctive or identifiable designs, and unique aesthetics on handmade items. In cases like this picture frame and artwork, we would remove the artwork itself, leaving just the picture frame, which arguably gives a more versatile and modular asset that can be used in different situations. To further support awareness and compliance, we've published detailed documentation on EDC on this topic that outlines best practices and explains the legal review process for scan-based content. Then we get to additive reconstruction. So sometimes capturing a complete scan just isn't feasible, either because parts of the scan aren't accessible or the form isn't ideal from all angles. In these cases, we use additive reconstruction, completing partial scans by carefully modeling or sculpting in additional details, merging scan data to form complete structures, always relying on scan data to fill the gaps. This additive approach helps us create complete and versatile assets. It ensures assets remain usable from various angles, expanding possibilities of creative world building and flexible scene assembly. By avoiding exposed mesh boundaries, you don't need extra geometry to hide gaps in your seams and your meshes, potentially keeping your project within budget. It also means that you don't have to limit player movement or restrict their view, preserving player agency. Then we get to texture reprocessing. So in some cases where it is impractical to scan with the flash scanner that I mentioned earlier, such as drone scans or large canyons, or in this case, a few stories up on a residential building. For large scans, it's impractical to use the flash scanner just because of the fall off of light, and we just end up not getting any real benefit from the flashes. So in these cases, we post-process the base color map to reduce any baked shadows, as we need to have a perfectly flat starting point to be able to relight in UE without being biased by the lighting conditions on the day of scanning. As we scan with a cross-polarized setup, which cuts out any reflectance values, we also need to enhance these assets by authoring physically based materials, including refined maps for specular, roughness, gloss, base color, and metalness. These additional textures help accentuate details by increasing the visual fidelity and realism of each asset in different lighting scenarios. So here you can see a difference between the raw photogrammetry scans and after they've gone through an artist-authored process. One of the things that makes scanned content so appealing for creators is the natural imperfections found throughout the world. But sometimes you just want to snap to a grid. So in modular workflow, we process these imperfect structures into precise grid snap meshes, allowing vertex snapped alignment and seamlessly tiling textures from one mesh to its neighbor. A lot of our architectural scans have issues with scanned glass, where you also have to remove all of that as well to make them more versatile. These modular assets seamlessly integrate with tools like PCG or any other parametric tool, enabling efficient and versatile asset creation. Compatibility supports easy integration into larger asset collections and modular building kits. And finally, a larger example showing all of the modular pieces for a building, which was scanned not in one go, but consists of around 15 pieces, which can be infinitely randomized with different layouts and building footprints to suit your needs. And we have multiple styles of building kits from different eras in our library as well. So now let's explore some of the refinements that we've been making to assets now that we're shifting our content to Fab. Our goal is to always enhance efficiency, consistency, and overall performance, ensuring that our assets are easier and faster for you to integrate into your daily workflows. To better support diverse use cases, we've introduced a new asset tier system, which is now available on Fab. Instead of traditional LODs, assets are organized into quality tiers. The highest quality tier is designed specifically for use cases such as in-camera VFX and nanite workflows, ideal for projects demanding maximum visual fidelity. While the lower quality tiers are tailored for platforms with resource or bandwidth constraints, mobile hardware, or projects where storage space is a consideration. In this example, you can see a comparison between a previous hero asset and its UEFN counterpart. This is no longer just an LOD, but rather a fine-tuned mesh with unique textures to suit its purpose. One of the key goals with the new tier system was consistency in asset complexity and detail. Assets of similar size and complexity now maintain roughly the same triangle count across each quality tier as illustrated here. This standardization helps to simplify optimization, ensuring that you get more predictable performance and visual quality when placing assets from the same tier into your scenes. Previously, our high-quality meshes received a lot of attention in mesh and texture processing, while LODs didn't really benefit from this as they were intended to be used way off in the distance. Now, each asset tier gets optimized textures that hold up well, even when viewed closely or used prominently in your scene. I'll go into more details on the tools behind some of these improvements later on in the presentation. As mentioned earlier, we also have higher material accuracy for our textures than ever before. We have based the artist-generated maps on measured spectrometer values for various metals. A spectrometer is a device that measures how materials reflect or absorb light at different wavelengths, providing precise real-world data to ensure accurate reference values. This provides artists with a lookup table as a reliable guidance when creating PBR maps for assets. And when it comes to displacement, one of the biggest pain points when using displacement is the need to refine and tweak scale and bias values in your shaders. If you have ever needed to tweak displacement shaders in your scene, you'll know exactly what I mean. We wanted to mitigate this by pre-calibrating our entire library across 3D, surfaces, and atlases to avoid having to spend any time worrying about this problem ever again. This calibration process gives us precise values that represent real-world distance that a displacement map represents. This then allows us to plug these values directly into the magnitude and center values in the shader and gives precise displacement values without any further manipulation. This removes any shader logic, which can be daunting to new users, and setting the magnitude and center is, at least at the moment, the most optimized way to work with displacement in UE. We provide two standards for our displacement maps. We have a 32-bit floating point EXR with real-world distances baked into the pixel values. These are zero-biased maps designed to be used with no additional offsets. We also have an 8-bit JPEG, which is normalized 0 to 255, which then makes use of the scale and bias values stored in the metadata to achieve the same mathematical range as the EXR, but with a fraction of the cost. Here we have this working on a surface example and Unreal on a landscape. For surface assets, it's important to consider the original scan dimension because the calibration relies on the asset's physical size. You can think of a texture UV tiling as the XY dimension and a displacement strength as the Z dimension. The assets will look their best when the tiling closely resembles the physical scan dimensions. These dimensions can be found in the metadata of every surface asset that we provide in the library. This principle also holds true whether you're dealing with small assets of around 1 to 2 meters or larger surfaces like terrains that can span several kilometers with hundreds of meters of displacement elevation. So as long as the tiling and dimensions are correct, the displacement values will work out of the box. One final note on this is that depending on your dicing rate that you set in Unreal, you may start to see stair-stepping artifacts when using the JPEG due to the 256 grayscale bands available in the texture. And then here's another example of the same surface, but rendered in Karma in Houdini using the EXR. In this case, the EXR was connected to the Material X displacement sampler with no additional values needing to be set, and this should be the case in most other DCCs. We now also support ambient occlusion for our 3D assets across the board so that there is just better consistency between different asset types. This is especially useful if you set up one master material that utilizes AO for your entire project and you need to seamlessly blend 3D assets with surfaces in an environment. Our team has also completely overhauled the vegetation library for Fab. We now have a nanite optimized version using high detailed geometry instead of opacity mapped cards to improve efficiency and reduce overdraw when using nanite. We have overhauled the wind response, vertex color system, shaders, and so much more. My colleagues Nils and Simon will have a talk focused on the future of nanite foliage, which I'd highly recommend if you want more details about this. That's happening tomorrow. So now on to some future-facing features that are yet to be released, starting off with calibration. We have gone through and recalibrated the entire library to have a more accurate lighting response. The goal is to create base color maps that are far closer to artist expectations and a big step towards more realistic visuals. This was a massive collaboration between the Quixel team and the rendering engineers and color scientists at Epic, and we're very happy with the improvement and believe you will be as well. When this does get released, we will include the correction factors used so that anyone midway through a project will easily be able to revert back to the previous calibration standard for any new assets that they download from Fab until they're ready to fully shift over to the new standard. Another feature which is easily overlooked is naming and taxonomy. As the library has grown over the years, we've seen a need to revise our naming strategy to make assets not only easier to search for, but also organize while keeping similar assets grouped logically together on disk and in UE. The naming scheme follows a hierarchical structure from broad to specific. This means that searching for a category of forest would now return all of the children categories of, say, Nordic, tropical, and temperate, and so on, allowing you to be a lot more specific in the assets that you're searching for. The metadata also improves abbreviated versions of the names, designed specifically to prevent character path limits in UE, but that still follow the global naming convention. So now let's take a look at how we handle Megascans production at scale, leveraging automation and procedural workflows in Houdini. We've developed procedural tools, cloud-based processing systems, and Houdini-powered workflows that streamline asset production. These advancements significantly reduce the number of manual steps and enhance consistency in our pipelines, enabling us to efficiently scale production while maintaining the high-quality mark of Megascans. So let's take a closer look at some of these key tools. So first up, we have a heat map generator. This provides an objective and quantifiable measure of scan quality. This tool serves multiple essential purposes. It clearly indicates to scanning teams where additional capture may be required. It also guides artists towards areas needing extra cleanup or attention during processing. It can enable early detection of problematic scans, saving resources by indicating when rescanning might be more cost-effective than repair. And looking ahead, we plan to utilize these heat maps as masks in machine learning-based tools to be able to automate and streamline repair processes. As you may know, generating high-quality UVs for assets can take a considerable amount of time. So because of this, we've developed our own UV generation tool to auto-unwrap complex assets. With this approach, we start at the individual triangle level, assigning each triangle to a patch of its own, and work iteratively outward, gathering neighboring triangles that satisfy some criteria into larger and larger patches. At each step, we query the characteristics of neighboring patches to determine which, if any, to join up with. By recalculating those characteristics when the patches merge, we can dynamically adjust our goals for the next round of merges towards reduced distortion when the resultant patches are eventually flattened from 3D into UV space. This UV layout can then be used either as a starting point for an artist to finalize or as the final UV layout for simpler models. Texture baking, for anyone that doesn't know, is the process of transferring mesh or texture information from a source mesh to a target. This typically involves the use of casting rays, collecting results, and writing an image. But occasionally, these rays are unable to return the right data, and when this happens, you end up with bake artifacts in the image. Typical baking processes involve the use of a cage, which dictates the direction and max distance that a ray can travel. This works well in very controlled environments or when an artist is able to author the cage. But we found that with the unpredictable nature of photogrammetry topology and the need for full automation, a simple cage approach was unable to fully envelop the meshes in many cases. Even with an iterative solver-based approach for finding the best coverage, there's still numerous cases of undercoverage leading to holes in the baked texture or overcoverage, which reintroduce the overprojection artifacts which we were trying to solve in the first place. So our solution to all of this avoids all of the cage-related limitations of skewing bake normals being tied to mesh topology, etc. And that was to develop what we call blocker meshes. So this two-sided geometry effectively is shown in blue in this diagram, wraps around both the red source and the green target mesh like a sock, and prevents pretty much all of the projection artifacts as the bake rays only have a single valid target for them to reach. If a ray fires in one direction and hits the blocker, then they simply retry and cast in the other direction, returning the correct result. After implementing this into our workflows, we've seen a dramatic decrease in the number and severity of texture bake-related artifacts during processing, resulting in way less artist time, if any, needed to clean these up. So in order to create clean UVs and game-ready topology, our workflow is designed initially to operate on much lower resolution meshes. Once this mesh is approved, it is run through an iterative subdivision and reprojection process to reintroduce all of the high fidelity meshes from the scan, which gives us perfectly optimized UVs on multi-million triangle meshes. So the project tool runs a progressive subdivide and projection operation. The tool is able to take a low poly mesh and iteratively subdivide and project against a much higher target mesh. So in these illustrations, you can see it looks like a poly reduction in reverse, but it's actually us projecting back all of the high quality details onto that base mesh. Very importantly, the iterative step includes error checking passes so that each round of projection can start on a very clean mesh. Therefore, bad projections don't compound over time. In naive solutions to this, a single bad projection on an early iteration can lead to a complete rat's nest of geometry that's very, very difficult to resolve after projecting over and over. So our ray logic avoids all of these types of issues. And then in order for us to hit the targets for the new quality tiers for Fab, we needed to develop an entirely new tool set that was able to quantify the complexity of an arbitrary input mesh. It's something that's very easy to look at a mesh as an artist and figure out the complexity, between 0 and 1. So we needed to figure out how to infer this in a system. So this process optimizes the triangle distribution of a mesh by running a decimation process across various poly counts and scores the results against specific criteria. Initially, the input mesh is cleaned and analyzed for characteristics like curvature, flatness, occlusion, thinness, as well as geometric boundaries to influence triangle retention during poly reduction. Candidates are then scored at different stages for topological complexity and surface area. This approach allows for adaptive triangle retention, meaning a mesh with high complexity can retain more input triangles. We at Quixel are committed to empowering fab sellers and the wider community by openly sharing our knowledge and expertise through detailed documentation on EDC. This ongoing effort helps partners, developers, and sellers upskill, providing clear guidance on creating content that meets Megascans quality standards. Our goal is to democratize the scanning workflow, ensuring the valuable insights that we've gained over the last several years are accessible to everyone and not just within our own teams. And that brings us to the end of today's session. Thank you to everyone who came to listen to today. And a huge thanks to my team, without whom none of this would be possible. So, thank you.